now. There we go. We're rolling. Very good. So people, please feel free to turn on your cameras if you would like to, if you feel comfortable. It's always nice to be able to see people paying attention, and I think it kind of brings people into the talk a little bit more, but please don't feel pressure to either. Fantastic. Okay, so we can get going. I guess there may be a couple more people to come along the way. But yeah, welcome everybody to the Shocklab seminar series. I guess we're probably on seminar number 7 or so of the series. We're extremely happy to have Geraud here from the Rail Lab at the University of Witwatersrand in Johannesburg. Geraud was previously at Rhodes University and is working on his PhD on lifelong reinforcement learning. And today he's going to talk about lifelong reinforcement learning through zero-shot logical composition. Over to you.
Awesome. Thanks for that nice introduction. Let me just quickly check something here with my battery and see. Okay. Awesome. So my main area of research is in reinforcement learning, and right now my kind of like more specific kind of interest is generally along the lines of transfer learning, and the kind of specific way we are kind of approaching this, at least for my research, is through the notion of composition. So we are going to get more into that. So like the kind of idea is that we want more efficient lifelong reinforcement learning agents, and the way we're going to try and achieve that is through composition. So let's see, reinforcement learning. So reinforcement learning is like this subfield of AI that has like huge success in the recent years. Many of you probably have heard of reinforcement learning agents being able to play Atari games at like very high competitive level. You probably heard of from DeepMind that beat the world champion at Go, and later on they improved that to be able to like play any like chess, Go, and shogi, all of that to grandmaster levels. And reinforcement learning is also been can be used to like learn robotic manipulation tasks. So huge success in a variety of domains, and this kind of gets close to what we ultimately want, right? Like we ultimately want like a single type of learning paradigm that can learn like a whole variety of tasks. But the issue is that just like human beings, so human beings, like if you give me one task that I haven't seen before and I'm trying to learn that task, I don't necessarily learn that task from scratch, right? Like we human beings, we are like a single agent that we are able to like solve this whole variety of tasks, and we're able to like leverage knowledge learned from past tasks to solve new tasks. But reinforcement learning, it takes considerable training time to like learn each task. It takes like billions, millions, and billions of training samples. So although it's like powerful, it is like at a considerable cost, right? And usually it's because it is learning from scratch. And yeah, so that is a problem. What we ideally want in this kind of like whole area is we want ultimately lifelong learning agents that are able to like efficiently leverage and solve new tasks by maximally leveraging past knowledge. So an example would be, for example, we may want to have like domestic robots that can like serve breakfast with a slice of white or brown bread with no butter, and it can just do that. It doesn't have to learn from scratch to do that, right? And if you change the instruction, it should be able to like do something like that. So ultimately, this is the type of agents we want, and there's kind of like two problems that you can kind of break this down to. One is actually understanding the instruction. So you give, for example, like an English language instruction, and the robots maybe needs to understand that, and you can kind of phrase that as being, it needs to be able to translate that into a formal language representation of that instruction, right? And that is like one problem towards that kind of like end goal, this instruction understanding. The second part is policy generation. So given that the robot knows what is the task it needs to solve, right? That instruction is given to it as a formal language, in a formal language representation. Then the question is, okay, now it needs to like obtain a policy for that. And there's several ways that people have been doing this in the literature. One way is by you are going to take a single neural network and you are going to just condition it on both the observations and the instruction, and you're just going to train that single network to multiple tasks like that, and hopefully it generalizes to like new tasks. So that is kind of one black box way of doing this. The other way is people kind of like take the formal language instruction, they use that to kind of generate some useful reward signal from that language instruction, and again, they use that to train their reinforcement learning agents to obtain a policy from that. So usually this is how people usually attempt this, and the problem here is that, so there's no guarantees about generalization, right? Like you kind of like trust the neural network to kind of hopefully from the set of tasks it has to learn to hopefully generalize to new tasks. But the way the approach that we are interested in is, given that formal language instruction, can we kind of somehow say that the agent learns a set of base skills, a set of like primitive skills, and then give it the language instruction, or like give it the formal language instruction, it composes those primitive skills, those base skills according to that instruction in a zero-shot fashion, such that it can immediately obtain the policy to solve that task. Right? So that this kind of like the approach that we are kind of more interested in, so that given a new task, it doesn't have to do any learning. If it has the sufficient amount of base skills, it should be able to just compose those skills to solve the new task. And we can kind of break down this kind of idea of formal language instruction to do social composition to obtain policies. We can kind of break that down into different types. But you can imagine that, okay, at the simplest level, our robot should at the very least be able to do combinatorial logic. Right? So if you ask your robot to, I don't know, pick up a cup of coffee without, or like make a cup of coffee without sugar, for example, then that is like a propositional logic type of instruction. And you can imagine more complex instructions that can be phrased in the family of finite state machines, where you have some temporal aspects to it. Right? Maybe you want your robot, you are in a office environment and you want your robot to maybe like pick up a cup of coffee, then deliver that to a given person in the office. It needs to do that maybe without hitting people along the way, stuff like that. So it's like finite state machine, and ultimately, at least in my thinking, ultimately what we want is Turing complete composition. You want a robot that you can give it any instruction, any computable instruction, and you just want it to be able to like just do some composition over a set of base scales and be able to immediately execute that instruction. So what this talk is going to be, so that's kind of like the kind of ultimate goal, I think. And once we have that ultimate goal, then the only kind of part which there's a whole line of work on is the instruction understanding part, where now we want to deal with natural language in the mix. But this is kind of like what I'm thinking of. So this talk is going to be focused on the minimum that we need, the combinatorial logic part. And yeah, so there's been previous work on this. So there has been works that attempted to do this union of scales, and this was actually done optimally by Stephen James, one of my co-supervisors, and actually my master's was I saw this work, and then that was like the inspiration for my master's research. It was like extending what they did there to now the full spectrum of Boolean expression, not just union, but also intersection and negation. So they did union, and other works separately with different approach did approximate intersection. So it was from Hanoja, from DeepMind, and Hunt, all of them from DeepMind. And approximate negation was also kind of like attempted in the literature, and this was also from Barreto from DeepMind. So this was kind of like what people had done before. And all of this done with separate approaches, but the goal is, so you want to be able to do this union, intersection, and negation using a single framework and in a zero-shot fashion, not just like approximate. Right? And the goal of motivation is that, at least intuitively, our robots should at the very least be able to do something like that. If you have any hope to kind of generalize combinatorially in the space of scales. Okay, so that's kind of like the idea. So I guess most of you are already familiar with reinforcement learning, but just for those who are not familiar, reinforcement learning is basically, the setting is you have an agent in an environment. The agent takes actions in the environment, and the environment gives back the next observation and a reward, like a feedback, scalar signal that tells the agent something about the action it has taken. And the agent takes that reward signal, it takes in the next observation, and it uses that to decide what is the next action. And it also uses that reward signal to kind of optimize its policy. Ultimately, what it is trying to do is going to be to learn a policy such that if it executes that policy in the environment, it is going to maximize the rewards it receives in the environment. Right? So that's kind of like the setting. And usually this is kind of framed using a Markov decision processes. And the Markov decision process is essentially a tuple where you have your state, that is S here, you have your set of states, that is S, you have your set of actions, that is A, you have your transition probabilities, that is P, and you have your reward function, which is R here. Yeah, and there's also this notion of value function. And the value function for a given state under a given policy is simply the expected cumulative sum of rewards in the environment if the agent follows that policy. So the goal of the agent is to kind of find a policy that maximizes this quantity. And that is what we call an optimal policy. Okay, so that is what the value function is. Okay, so let's take this simple domain. This is the domain we are going to be using throughout this talk. So here you have an agent. You can take like up, down, left, right actions. There's multiple objects in the environment, different shapes, different colors. And let's say the agent has learned how to pick up blue objects. So it has a value function for that. So we can see here, for example, for the blue object, we see the value function at each position is it kind of like gradually goes towards and it picks where the blue square and the blue circle are. So that is a value function that it has learned for this task. And you can use that value function to like pick the optimal action to take in each state. And it also learns, let's say it has also learned how to pick up squares. So that is a value function it has learned for that. Okay, so when I speak of scales here, I will be speaking of scales are value functions. Right? Scales is what the agent has learned. It has learned value functions, and it can use those value functions to act in the environment. So given that the agent has learned these scales, the question is, can we compose these value functions to solve any task that is a logical composition of the blue and square task without further learning? So that is kind of like the question we're trying to answer here. An example is, can it pick up blue objects or squares, but not blue squares? So like the exclusive of blue and square. Can it do that without further learning? So that's what we're trying to achieve. Okay, so the first thing we need to do is to formally define what we mean by logics over tasks. Right? So we know propositional logic, we know logic in like set theory, where you speak of intersections, unions. We know logic in terms of digital secures, like all of that. But we need to define what do we mean by this intersection, union, and negation over tasks, over MTPs, right? So the way we define that is straightforward. So I mentioned earlier that tasks in reinforcement learning are represented as Markov decision processes. So what we are trying to do is define these operators, intersection, union, negation. We are trying to define that over MTPs. And the way we are going to do it is straightforward. So for the union, for the OR, that is just going to correspond to the MTP where the reward function is just going to be the max of the individual reward functions. So the R of blue and square is just going to be that's where its reward function is going to be the max of the reward for the blue and for the square task. And similarly for the intersection and negation. So intersection is going to be the mean of the reward functions, and negation is going to be this constant minus the reward function. The constant is like R max, which is the maximum possible reward in the environment, and R min is the minimum possible reward in the environment. So that is basically the bounds of our reward function in the environment. So that's how we will define these operators. And if we restrict the rewards at the goal state, then we can prove that this forms a Boolean algebra. It satisfies the axioms of a Boolean algebra.
Sorry, can I just ask a very naive question here? So if you just go back to that last one, yeah. So here this is saying you're picking up something which is blue with picking up something which is square, and it's an or there, which essentially is like giving it the instruction, I would like you to pick up something which is blue or which is a square. Yeah.
Yeah.
So then a return of either of those would be correct.
Yeah.
Right?
Yeah.
Why does one, yeah, I think I'm just being a bit naive here. Why does one necessarily have to take the maximum over the rewards? Because presumably if the reward for, let's say the square was lower than that for the blue, it would still be fine to pick up the square. It would still satisfy the request.
Yeah. Good, very good question. So the reason for that is because what the agent is trying to do is it's trying to maximize rewards. Right? Mm-hmm. So if you imagine, for example, that if the agent was here, then the correct thing to do for the union, if it's going to be maximizing rewards, should be to go to this blue square. Mm-hmm. If the agent was here, then let's see, if the agent was here, then the correct thing to do would be to instead go to this square is not blue, but it is closer to a square that is closer to a blue object. And so the correct thing to do should be to go to this square here for the R. So that is why it is the max, because we want the agent to optimally satisfy that condition. We want it to optimally reach a blue R.
Okay, so really the statement isn't that isn't just pick up the blue thing or the square, it's pick up either the blue thing or the square, whichever one gives the largest reward.
Exactly, yes.
Okay.
Yeah, that's a very good question. Okay. Actually, if anyone has any question along that as I'm going through the talk, please just feel free to ask. Good. Okay, so now we have defined what we mean by logics over tasks. Now we want to see how do we compose our value functions to be able to solve this task. So if you have learned the scale for blue, you have learned the scale for square, you have their value functions, and now we are trying to obtain a value function for let's say a blue squares. Then how do we do that? Now you have a way of measuring actually if our value function is actually the optimal value function, because we know the task that corresponds to the blue square task. So you have the value function for the blue task, you have the value function for the square task. How do we compose this value function to obtain the value function for the blue square task, right? For the intersection. Oops, I don't know why I'm thinking automatically going forward. I'll reveal the answer, hopefully, well, not the answer, a possibility. Hopefully no one saw that. Yeah, like I guess if you are posed with this question, maybe there's a couple of things you may think of. Okay, so let me just repeat the question again. So you have the value function. The value function is basically just like so for each state action, it has like it's a real number, right? So you have like this function, this real valued function for the blue task, and you have the same thing for the square task. And the question is, what operator do you apply on both of those functions so that what the function you obtain as a result is going to be the correct function for the blue square task? Now, maybe people, does anyone has any opinion there, any suggestion before I give possibilities?
Does it have to be a Boolean operation?
No, any operation. Like our goal here is we want to be able to get the value function for the blue square.
And a product won't do it.
Yeah, nice. Yes. So product is a good suggestion. Right? Another good suggestion is average. Another good suggestion is mean. Right? Those are kind of natural things we may think of. It turns out that none of those work. Right? So if you do the product, if you do the averaging, if you do the mean, actually all of these ideas are actually properly defined intersections in fuzzy logics, right? In revalued logics. But in this case, where the result that we want to obtain needs to be a value function and not just any revalued function. It needs to be the revalue function for the blue square task. We actually run into an issue, which is, so here I'm showing for the mean, but we get something similar if you do averaging or if you do product. And we see here that, okay, so the blue square is on this corner. Oops, the blue square is on this corner here. When I do the mean, and again, it's the same thing if I do the product and averaging, we see that, okay, around the upper diagonal or the lower diagonal here, you see that actually the value function it looks good, right? If the agent is anywhere here, then the best thing to do would be to go to this blue square here, which is correct. But on the lower diagonal or upper diagonal side, if the agent is anywhere there, actually will be doing something funny there. It won't be doing the correct thing. So if the agent is, for example, and hopefully I guess you guys can see my mouse. If the agent is here, then it's actually like at the local optima there, and it's going to get stuck there. And why? Because what you actually have is a I don't know if you guys can see this clearly in the figure, but you have like a beige square in the corner here, and you have like a blue circle in the corner here. And so if I do the mean, then when the agent is here, it's actually confused where to go, right? Because it has like equal distance between it. It has like a square and it has like a blue thing. And if we do the average, what we get here is like a flat, it's like a flat graph. And if we do the product, it's going to be similar to this mean, just like the less picky optima. Okay, so why do we have this situation? Actually, so the reason for that is actually because when the agent is here in this region, it actually has no information about the common goal, which is to go to this blue square. Why is that? Okay, so for when he was learning the blue square, when he was learning the blue task, at that position, all it cared about when he was optimizing, trying to find what is the optimal policy for that task, all it really cared about was, if I am here, what is the value with respect to the nearest blue object, right? So all it learned when it was trying to find the optimal policy, all it learned was that here, the correct thing to do was to go in that direction to the right, because that is where a blue object is. It didn't learn anything about this blue square if it is in this position, even though that is a blue object, just like disregarded that in its optimization process. Similarly for a square, right? If the agent is at that position, it learned nothing about this blue square here. All it learned was that, oh, actually there is a square nearby. So the best thing to do here is to go to that square that is nearby. It has no information about any other square in the environment at that position. And that is why there's no information about the common goal here. And in general, no operator over these two value functions will be able to give you the correct value function for the blue square task because of that common goal issue. Okay, so there is so actually what previous work did when they were kind of trying to find approximate solutions to this is they use an operator. In the case of previous work, they used the averaging, but you can imagine you can use the product or the mean. They did that, they obtained an average, an approximation of the value function like this one. And then what they did was then they could do further learning to kind of fine tune that value function by using a divergence information, right? So you can see this value function, you can see that value function, you can kind of like measure the divergence between those two value functions, and you can use that information to kind of know where you kind of want to, where you need more fine-tuning on the value function. And that way, quickly update the approximate value function to get something that is actually doing the correct thing everywhere in the state space. So that was like a very good approach. But what we want here is we don't want to do we don't want to approximate then fine-tuning, because that still requires learning. We want to do zero-shot composition. And so how do we do that? Okay, the solution is basically from this realization that actually what we were learning originally doesn't encode sufficient information to do this type of composition. You actually want to learn more when we are learning tasks. Okay, so this is what I've already said. So regular value functions are insufficient for zero-shot intersection. Okay, so how do we solve this? Just look at the time. Okay, so the way we solve this is by introducing a new type of value function, a new type of goal condition value function for a single task. And the way we do that is, so if some of you are not familiar with goal condition value functions, they're essentially value functions that are conditioned on both state and goals, right? Except that in the literature, usually the goal corresponds to the task. So you have the reward function for that goal given to you by the task. Here, the only thing that is given to the edger is the current state and the reward for that state. There's no notion of goal. There's no notion of the goal it needs to try to reach right now, or the specific goal it needs to try to reach right now. But somehow we kind of want to say that during the blue task, for example, it needs to not just learn how to reach blue objects. What we actually want it to do is learn how to reach any object in the environment and learn the value of doing that in that given task. So that is what we are trying to do here. And the way we are going to do that is simple. We are going to say, okay, we are going to define the goals, the set of goals as being the set of terminal states in the environment, the set of terminal states in the environment. And we are going to define the value function for each state goal as being the same definition as earlier, except that the reward function is also going to be conditioned on the goal. And the way we are going to define this goal condition reward function is by just adding one piece of information to the reward function definition, which is, so RSA here is the regular reward function the environment gives the agent, or it's a regular reward function for the task. We are going to say that the goal condition reward function is going to be that regular reward function everywhere, except when the agent reaches a goal that is different. So when the agent reaches a goal, so a state that is an element of the goal space that is different from the goal it was trying to reach. If it reaches a goal that is different from the goal it was trying to reach, then it will give itself a large penalty when it does that. And that is it. And the idea here is that every time it is trying to reach a goal, the optimal thing to do will actually be to learn to reach that goal, because if it doesn't, then it will be receiving large penalties. And it doesn't want to receive large penalties because it's trying to maximize rewards. Right? And with that simple modification, what we now have is that, again, with the exact same information from the environment as before, we can now learn a more useful knowledge representation. So now for the blue task, the agent learns how to achieve every goal in the environment. And not just that, but it learns the value of achieving those goals for that specific task. Right. So we can see here, so here I'm plotting the value function for each goal it has learned for that task. And we can see here that the values for example, purple square, purple circle, all of that are low, while the values for blue square, blue circle are high because it received high rewards when it achieved those goals in the environment. Right. So it learns how to achieve all of the goals in the environment, and it learns the value of achieving them for that specific task. And once it has learned that, so now you have like a more richer knowledge representation for each task. And once it has learned that, okay, we still want to be able to solve the task if we want to, right? Like now you have this, but how do you actually pick actions with this more complicated kind of knowledge representation? The answer is simple. We just maximize over goals and maximize over actions. So if we maximize our goals, we actually provably recover the regular value function if we maximize our goals. And maximizing our actions, we can then like pick the best action to take at each state, right? So modification on our reward function doesn't give nonsense, right? We can still recover the regular value function that people usually learn in reinforcement learning. We can still recover that from this knowledge representation by just maximizing our goals. But now the knowledge representation we have is like this type of richer knowledge representation, which is what we are going to see soon actually makes composition possible. So similarly for the square task, we can learn the extended value function, or the way we are calling this is extended value functions. So if we learn that for the square task, maximize over goals, you recover the regular value function for that task, and you can maximize over actions on it to pick the correct action to take in the environment. Okay, so does everything make sense so far? Does anyone have any question with respect to this?
Sorry, I have a quick question. So for that top figure, the extended value function is learned for all goals, but you're so you're training for the blue task, but you're learning over all colors and shapes. I'm just a little bit confused what you mean by that. So when you're training the extended value function for the blue task, are you cycling through goals, or like how exactly are you doing that learning process?
Yeah, so the way that is done is, okay, so first the goals. When the agent is like navigating in this environment, when the agent is like navigating, so in reinforcement learning, the way the agent learns is like through like exploration, exploitation. So the agent is going to be like via trial and error, going to be navigating the environment, and then using the rewards it sees to kind of like update its value function. So let's say the agent navigates in this environment and then kind of like stumbles upon this object here, and the environment is going to terminate, and it's going to receive, okay, if it was the blue task, it's going to receive a reward of -1, for example, right? What we are going to do is that we are going to, so that's the terminal state, we are going to add that to our set of goals, right? So like we are going to learn goals by saying, like when the agent kind of reaches terminal states, that is how it learns. It learns what is a set of goals. So that is the first thing. The second thing is that for each episode, the agent, for each episode, the agent is going to give the agent, the environment is going to give the agent what is the current state. And normally the agent is going to, given that state, is going to like pick an action, either randomly or like using its policy. But what we are going to do here is we are going to sample a goal from our goal, from the goal space we have learned so far. We're going to sample a goal, and then we are going to, for that state and for the goal we have sampled, we're going to choose an action to take in the environment. Right? Okay, so that is how we learn the goal space, and that is how we navigate in the environment. We sample goals and we try to reach those goals. So for each state and goal and action, the environment is going to give the agent this reward. All right. So for each state, for each state and action, the environment is going to give the agent this reward, and then we are going to modify that reward this way for whatever goal the agent is trying to reach currently. Right? So the agent sample its own goal that it's trying to reach. If it successfully reaches that goal, then all of the rewards it will receive during that trajectory is going to be the regular environment rewards. If it reaches a goal that is different from the goal it was trying to reach, if it reaches like a terminal state that is different from the goal it was trying to reach, it is going to give itself a large penalty. So that is basically how the agent interacts in the environment during learning. For each state goal action pair, we just use regular reinforcement learning algorithms to learn the value function for that. So something like QO learning in the tabular case, or something like TQN in the functional approximation case. So that is how the agent, for that task, where for that blue task, where normally the environment gives it the current state, the agent picks an action, and the agent learns the value and the value function. We modify that with this goal, and that is how. And the goals are learned by exploring the environment. The agent acts in the environment by some goals. For each state goal action pair, the agent learns the value for that using this reward function. So that is how it learns this quantity.
So every episode, you sample a new goal randomly from the goal set that's been discovered. So then my next question would be, on the next slide you show the difference between Q blue and Q square. Wouldn't those value functions be the same because they're trained in the same process and they're trained over goals that are sampled from a discovered goal set?
Good question. So in the blue, when the agent is in the blue task and it reaches, let's say, let me pick this guy here. So there's a blue circle in the corner here, right? So the agent is in the blue task and it reaches this blue circle. In the blue task, it is going to receive a high reward. It's going to receive like a reward of 2 for picking up a blue. That blue circle. In the square task, it is going to receive -1 for picking up that blue circle. Right? So like in the blue task, it receives high rewards for picking up blue objects. In the square task, it receives high rewards for picking up squares. So so that is why the extended value function it learns for the blue task has high values for the blue goals, for the blue square and blue circle goals. Meanwhile, for the square task, the value function has high values for the square goals. And again, remember that the reward function we're using to learn for each goal is the environment rewards everywhere, except when the goal the agent has chosen is different from the goal it was trying to reach. So that means that if the agent correctly is trying to reach the blue square and it correctly reaches that blue square, it will receive the high reward for that or the low reward for that the environment gives it, right? So the way it is actually learning to achieve the correct goal is via this penalty kind of like term you have added. That is how it learns that if I'm trying to reach the blue square, I am going to, no matter whether that blue square is desirable or undesirable for the current task, I have to still try and reach that blue square, otherwise I will be receiving this large penalty.
Okay, I think I understand. So even when, even when you're conditioning, let's say you're training for the blue task, and you sample a goal which is for that one episode, which is beige square. Would you still give a positive reward if it collected a blue like a blue circle in the training of the blue task? So that diagram of Q with the blue task, is that the extended value function conditioned on the blue goal?
So this whole diagram here is the extended value function learned during the blue task. This blue square graph here is the value function for that specific blue square goal that the agent learned during the blue task. This purple circle graph here, which is hard to see, but it is like below 0 here. This, because so you can basically imagine, so the function approximation is like a new log. It takes in the state observation. The state observation is like basically images like this one here. It takes in that, concatenates that with the whatever goal observation that the agent has sampled from the discovered goals, concatenates that, and then that is what is passing to the neural network. So what I'm doing here to plot this graph is that I'm taking, for each position here in the environment, I'm taking that image. I am taking each goal in the goal buffer that the agent has discovered. So like for example, for the purple circle, I take the purple circle goal, I concatenate that, and then I pass that to the neural network. So that is how I'm plotting this graph. So it is like a single neural network for this blue task. And to plot each graph here, I'm just like, say for the current observation, I pass it each goal, and then I say what is the value for that.
Yeah, I see. Okay, thank you. There's just one thing that I'm missing, but I'll ask afterwards, and then we can talk about it.
Yeah. So can I just ask you a quick question here? So to get the extended value function, you're ending up with essentially more information than you would if you were just trying to calculate over the blue value function. Yeah. Does it take more observations to do that, or do you have to run the same number of observations and you get, you know, in the end you get the picture on the right, just the blue value function? Because it looks like you're having to do more computations, which is kind of what you're trying not to do because you want to do zero-shot learning in the end.
Yeah. So that's a very good question. So there's a trade-off here, actually. There's a trade-off in how much time do you spend in learning each task, and how much do you get out of that in terms of future transfer learning opportunities. So in the paper for this, we actually have graphs showing that basically it takes like much longer to learn this extended value function than learning the regular value function, because of course you are learning more and you need more samples to do that. But then, because, okay, so after this slide, I'm going to show that actually this actually gives us, when we compose this, we're actually able to do zero-shot composition with this. So when you look at the trade-off with the exponential combinatorial of amount of scales you get when you compose these value functions, you actually get like depending on the number, on your space of tasks, or like the number of goals in the environment, you actually get like a nice trade-off that if you're not interested in composition, if you're only interested in like learning this specific task, then this is not worth it, right? Because you are spending more time learning this task. But if you're interested in being able to learn tasks and be able to compose that knowledge to like get this combinatorial amount of skills, then you get a trade-off that the amount of time you take to learn this skill is like approximately polynomial with respect to the regular value function, but you get this exponential benefit in composition.
So it looks in a sense like the extended value function should give you everything that you need to know. You shouldn't need to do any sort of combinatorial stuff afterwards, in the sense that, you know, if you wanted to do a blue square, you've already got the value function for blue square there. You've already learnt it. So it's not like you need to take the extended value function, calculate the Q value from that of blue and from the other one of square, and do any composition. Haven't you got everything already?
Yes. So you basically got everything already in this. Like you basically have all of the policies already encoded in this value function. And so if you know like the goal, like if you know, for example, the goal you need to achieve right now is the blue square goal, then there's no composition needed. You just like, you can retrieve what is the correct policy for that. If you don't know that, if all you know is that the current task that you want to solve is like blue intersection square, right? You don't know the set of desirable goals that you kind of like, that defines the task. All you know is that you have learned the blue task, you have learned the square task, you want to do blue square task. Then that is where composition comes into play. Yeah.
Okay.
Yeah.
Can I ask a question quickly? Sorry. Hi, Joe. So do you know all of the goal states in advance? I think you might have said this already, or do you have to rely on exploration? Do you have to go through a process of discovery? Because I imagine, I mean,
you have to go through exploration.
Okay, so
because
also,
we don't,
sorry,
because we don't assume, like, we assume basically the same knowledge that regular reinforcement learning has, right? So we don't assume that you have any extra knowledge on top of that, other than you are in a given state, you take an action, you get a reward, and somehow from that you need to learn this.
Okay, interesting. So and then I suppose, yeah. So that, I mean, that's also an extra. You need I mean, I suppose exponent. I mean, the larger the state space grows, the more computation you need to be able to eventually find those as the terminal states as well. Because you'll be. I mean, you can only sample from terminal states you know about.
Yes, and the interesting thing actually with respect to that point is that actually even the regular, like this regular value function, we actually still also have to like discover all of those goal states to even be able to like know which is the kind of like high rewarding goals to try and reach. Right, so you still have that same issue, even if you are learning this like simpler reward function. So you're actually kind of making the most use of the samples you were having in the regular value function and making the most use of that to actually learn more with the extended value functions. Yeah. Awesome. So given this, where am I? Given this, we can provably show that applying this to the same definition of this intersection, union, and negation that we use to define logics over rewards or over tasks, we can use the exact same definition. So union, so OR is going to be max over the value functions, and is going to be the mean, and not is going to be this constant minus the value function. We can provably show that this satisfies the Boolean algebra axioms. What that means is that we can probably do any logical composition of scales, and we will recover the optimal value function for that.
Sorry, can I ask it here again, maybe a very naive question? So you've got the same expressions here that you had before, but to calculate Q of blue, you went through a different route. You first calculated the extended value function, and then you use that to give you Q of blue.
Yeah.
So is this Q of blue different from the original Q of blue?
Yeah, this Q of blue is the extended value function. The original Q of blue was the regular value function. And if you wait, maybe actually you are talking about here. Mm-hmm. So here when I here this blue here are not the Q values, they are just like the task.
Yeah, thank you. No, that's exactly the answer. Thanks.
Awesome. So yes, so now if you want to do blue intersection square, then we just take the extended value function we have learned for the blue task, same thing for the square task. We take the mean over that, and we actually get the extended value function for the blue square task, and then we maximize over goals. We get the regular value function, and then we can maximize over actions to act in the environment. And so if the agent is, even if the agent is like near a blue object, you still know that the correct thing to do is to go to the blue square. Yes, and to kind of have an intuition of why this kind of, I mean, like if it's not kind of already clear why this min, max, and negation stuff works now, we can see, okay, so we saw earlier that the value function that we have now learned encodes actually already the policy for all of the goals. And so all the min and max are doing now is just scaling up or scaling down the relevant values. So for example, for the min, intersection is saying what? Keep the value function that are common in both tasks. Right? So if you look at the blue extended value function, and we look at the square one, only the blue square value function is the highest in both of those extended value functions. And so when you take the mean, only that one is going to stay high, and all of the other ones are going to drop below. That is why that works. Similarly for the max, if we take the max, then all of the ones that were high in either one of those value functions will now be high. And when you take the max, when you maximize over goals, you recover this regular value function where you can say that the peaks are over all of the squares and over all of the blue objects in the environment. And the negation so all the negation does is if the value was high, it's going to like send that low, and if the value was low, it's going to send that high. So when we do that, maximize over goals, now the agent is going to go to objects that are not squares, right? And now that we have all of those three operators, we can do any logical combination of them. So for example, for the exclusive OR, we apply those operators, and now the agent is able to like go to objects that are blue or squares, but not blue squares. So if the agent is here, the blue square is closest to it, but it's still going to go to a object that is not a square that is not blue. Awesome. So we can do any logical composition of scales. And yeah, so this gives us a super exponential amount of scales for the number of scales we learn. So here I'm basically showing if you don't do any transfer, and this graph is the y-axis is in log scales. If you don't do any transfer, then all you can do in terms of scales is just the ones you have learned. So if you learn k scales, you can only solve k tasks. Before this works, so I mentioned that Steve and some other guys did a union disjunction optimally. So if you only have disjunction optimally, then you get this exponential amount of scales, because you can do like any disjunction of k tasks, and you get to the k scales from that. If you have the Boolean task algebra, then you can do any disjunction, conjunction, and negation of those scales, and what you get is a super exponential amount of scales from that.
Sorry, can I ask? Sorry, I've got lots of naive questions today. So let's say you've learned 2 tasks. So it looks here like you've got somewhere in the order of 100 solvable tasks, 50, 100 solvable tasks, something like that.
So if you learn 2 tasks, then you have like 16 scales. Yeah.
Okay. Is that obvious? How to enumerate the 16?
Yeah, because it is.
No, sorry.
Yeah. So it is. You can kind of imagine that as like a Boolean table where you have like two base, like 2 columns, and then all of the possible combination of those 2 columns is like 16 of them.
Okay, so you got two to the 2 to the k. Okay, perfect. Yeah, it does make sense.
Yeah.
Great.
Yeah. Awesome. So
sorry, I have another quick question as well. So that explosion is crazy to see, which is in a good way. That's really, really cool. But I mean, I guess what's maybe slightly a practical question of how many tasks would be kind of irrelevant in a practical sense. If you know what I mean. So like the task space that you can cover is massive with this method, but the relevant tasks would the combination still be worthwhile? I mean, I guess it depends on the problem setting. I'm not sure if you've done any kind of like investigation in that.
Yeah, it depends. It depends on the problem. It depends on the problem setting. Because you can imagine, for example, that for some problem setting, maybe you could do the composition and then you get the scale for reaching a given goal, but actually that goal is not reachable. No matter what you do, it's not reachable. So in that case, you have the scale for that, but actually it's useless because that's not solvable. But of course, like that is that. Not there's nothing you can do about if you cannot reach the goal state that you have to that you are required to reach. In the case where so that is one case. So like this kind of is kind of only showing if you have to solve like this task and you do like you learn like the value function for that. Like instead of learning the value function for that, you can get the value function for that from composition, and then it's a completely different matter if the task that you were required to do is even if it is doable in the first place. That is one aspect. The other aspect is useless. The other aspect is like useless compositions in the sense of maybe there's like blue intersection red, for example. and that is like meaningless, right? There's no blue object that is also red.
Yeah.
But that is not, so that is excluded from this number, because what we are showing here on the x-axis is base task. So you can so it doesn't include like useless compositions in that sense. Yeah. I see a hand.
Sinjin.
Yeah, so I'm on my phone, so I'm not sure if you can see me. But yeah, I'm sort of thinking about how exactly are we defining skills here? I know it's a bit of a naive question as well, but is the skill like some base level abstraction of a set of actions? And how does that differ from maybe something like an option in RL, where you kind of generalize out of immediate actions in one time step, and maybe a skill is several actions in a row? And that sort of comes together with this exponential idea of combining skills. Are we assuming a prior that the skills are disjoint completely? Because I'm sort of thinking about, let's say you have colored boxes, and you've got your base level colors, but actually some colors are combinations of other colors. So maybe, you know, being a purple box simultaneously satisfies being a blue box. How do we know, how does our agent know how to distinguish between these skills and whether or not they overlap?
Okay, so for the very nice question. So for the first part of the question, so options, you can basically think of options as scales. Okay, so what we're defining here as scales is value functions, right? So you can kind of think of options as scales with an additional notion of an initiation set and a termination set. So where you want to start using that option and where you want to stop using that option. So in that sense, you can imagine that this case here, you can kind of like define them as options if you want to use them in the context of like temporally abstracted actions. So that is, I don't know if that kind of answers that question. So like the scales here are defined as value functions. So for example, for the MGP with the given reward function corresponding to like the blue task, the value function for that. When you learn to solve that blue task, you learn a value function. We are calling that value function a scale. And if you're in the context of that, you want to do temporally extended tasks, like maybe you want to like pick up blue squares, then you want to pick up circles and so on. Then one way of doing that is using the optional framework, where you're going to define or learn this notion of initiation and termination sets for each scale. So that is one thing there. For the second part of the question, that is kind of like close to what I was what I mentioned earlier for the previous question, in the sense that this number here does not include useless compositions, in the sense that if you have like goals that overlap, in the sense of maybe blue squares, okay, so now we are calling it blue and purple, but let's just say for the sake of the argument, blue squares are also purple squares. You cannot distinguish between them, but they are like but you have learned separate value functions. You have learned like separate value functions from them, and then if you do that composition, of course, the composition is not going to give you something new, because they were basically the same. They were basically the same thing. That type of composition, that type of situation is not included, is excluded from this number here. So this number here actually represents truly different compositions of base case, and that's what is called base case. So these are like the minimal. So for a given task space, what is the minimal set of scales that spans? Well, I'm sure, but I'm speaking in terms of in terms of Boolean compositions.
Presumably, it's as if you think you learn to pick up red boxes, you learn to pick up square boxes, but you don't separately learn to pick up red square boxes.
Yeah, exactly. Yeah.
And also, I think this method's a lot better than options, in the sense that by representing skills as extended value functions, you're essentially, in the composition process, you're learning one full novel new skill that can accomplish both. It's not like it's kind of sequentially choosing primitives, which is great to see. I mean, it's quite similar to the successive features idea, except it's not so reliant on GPE and GPI, and it's just composing them with some function, which is kind of crazy.
It's very good point to mention, because features is kind of like one I would say competing line of work to this one, and this is, I mean, like we can have like more discussions about this, but we sound biased right now, but like this is kind of like less trash than successor features, and we actually have provably optimal compositions by learning these extended value functions, and successor features have like several issues with them. Not that this one doesn't have like its own issues, but yeah, that's a fun discussion. I feel like I am out of time. Should I quickly just mention like a couple of important points?
Sure. I think a couple of people have had to drop off, but we're recording this, so we can still go on for another few minutes if that's okay for you.
Yeah, awesome. Yeah, I'm happy with that. Okay, so this graph is just to say that, so we have done a paper where we showed that we can, okay, so I mentioned here that, okay, so you learn this case, you are told that, okay, now you want to do like blue square. So you're given that expression, and then you can solve that task. I know that the task that needs to be solved right now is the blue square task, because you are told that. But then in the context of lifelong reinforcement learning, where you have like this distribution of a task, and your agent receives like one task at a time. It needs to learn to solve that task, and then it receives like a new task sample from some unknown distribution, potentially non-stationary. And so it doesn't know, like, all it receives is current state, reward. It doesn't know like what is the expression for the current task. It doesn't even know whether that current task can be expressed as a composition of previously learned tasks. So in a setting like that, how can we leverage this idea of composition to kind of like generalize quickly over a distribution of tasks? And we showed that we introduced an approach that shows that we can effectively, for each new task sample from whatever distribution, we can determine whether that task is expressible as a Boolean composition of like previously learned tasks. If it is, then we can determine what is that Boolean expression, and we can compose our value functions to effectively solve that task with that further learning. And if it is not, then we can at least we can still do the composition using the estimated expression that we have obtained, and get an approximate value function for that new task, and then use that to speed up learning for a new scale for that task. Once we learn the new scale for that task, we add that to our library of scales, and we continue like that. By doing that, we get that. So for example, here, there's like about 40 goals, which is about 1 trillion tasks in the task space. Here we are sampling tasks uniformly at random, and we observe that after learning only about 15 tasks, the agent generalizes over the entire task distribution by using this approach. So that just got like the main thing to say here. We're also showing that if you use a worst case distribution for this approach and the best case distribution for this approach, you still get that it is upper bounded, like the number of scales you need to learn is upper bounded by the number of goals in the environment, not the number of tasks in the environment. And so that is kind of the main point there. Oh yeah, so with that, we get combinatorial logic, which is what we were trying to do from the start. And now that we are able to do combinatorial composition, Boolean composition of scales, we have, so like this is a workshop paper that we did recently. We are working on extending that to a full conference submission. But essentially what we did here is now we introduced natural language into the picture. We have that the agent, each task is like the agent receives a natural language instruction, and it needs to learn to translate that natural language instruction to the correct Boolean expression and then compose the scales to solve that task. And we show that in a setting like this, we are effectively able to like learn this translation. So we use transformers for this. And we show that using a pre-trained transformer, after learning just one task on average, after learning just one task, like for example, pick up red boxes, the agent is able to like solve any other future task zero shot. So it generalizes extremely fast. Using a non-push run transformer, it has less of that ability. You see how that generalization in terms of learning these translations, using the compose case to act in the environment, but the generalization is not as steep. Now we are working on doing this end-to-end because what we did here, we had to first pre-train the base case. So like pre-train the scale for blue objects, for picking up squares and so on. Now we're trying to see if we can do all of this end-to-end. Yeah, so I'm going to just quickly skip that. So we can do zero-shot logical composition. It gives us super exponential explosion of scales. We can use that for doing like safety constraint task execution. Maybe like you want to like make coffee without milk. If someone is allergic to milk, for example. And this is the first step towards being able to do zero-shot temporal logics. And actually, I didn't include this in this presentation, but we actually just did that. We have an archive paper on that, and it is currently under review for RCLR. And yeah, thanks for the opportunity.
Wonderful. Thank you so much, Geraud. That was fascinating. So yeah, lots to think about. Some clearly very important ideas. Are there any questions?
Yeah, I have another question. I've actually been reading a lot into this space for the past few weeks, and I actually would love to hear your. This is amazing work, and I really would love to hear your opinion on what you were saying on why you think this direction is a better direction than like DeepMind's FOST reinforcement learning updates with generalized policy evaluation and generalized policy iteration. The one critique I had with the presentation, which then you completely blew away my critique because you had that slide saying that you developed some way, you skimmed over it, but you developed some way of essentially inferring the Boolean composition from a general environment from some reward function. So that pretty much makes this method seem to be better than successor features in general, because you're giving, as you said, provable optimal composition, and you can infer the task. So do you mind just maybe, if you have time, elaborating on why on what you think the advantages of this method are compared to the successor feature method?
Yeah, so maybe let me first start with the disadvantages of quarterly. Or like, let me start with the disadvantage with my currently. So I mentioned that inferring the Boolean expressions part, but like that was done. Like they say some work that needs to be done there because they made some assumptions for that paper. And mainly the main assumption was that the goal space is finite. So like you can have like however big goal space you want, however big task space you want, but it needs to be finite. And that is basically a constraint we added just because because of two reasons. So one was because of our current functional approximation approach for extended value functions. And second was to have this nice upper bound on the number of scales you need to learn. So if your goal space is infinite, then your task space is infinite, and there's no upper bound in the number of scales you need to learn. But you still get like this exponential kind of like benefit as training as the number of tasks you see in your lifetime increases. So that like one point there. We can use that this to be extended for future work. The second point is which is kind of like so this kind of correlates with successor features is weighted is like linear preferences over scales. So far all of what I've spoken about is like Boolean composition. It didn't include any, like for example, if you want to have linear preferences, like maybe you want to pick up blue squares, the preference of, let's say, 0.8, and you want to pick up red circles, the preference of like 0.2. This didn't include that, but that is something that can be added to this framework in future work. So the reason why I mentioned those two disadvantages is because successor features do have linear preferences, right? Because they have like you are learning these successor features, and then you can do a linear combination of them to get the solution, the value function for a new task. And they do apply to continuous goals environments, except that, so the corollary there in terms of limitation is that their features still needs to be finite, at least for the current functional approximation approaches for successor features, because you need to be able to, like, the same as in our case, the goals need to be finite because we need to be able to maximize over them in an efficient way. Successor features need to be able to do generalized policy improvement, need to be able to maximize over the dimensions of features to be able to do generalized policy improvements. So that is one kind of different type of limitation. The kind of second thing is yeah, okay. So let me go into the main limitation, which I say is successor features, and that is it comes in two parts. One is the requirement that the reward function needs to be linear, right? So to me, that's like a very strong assumption that successor features make. It assumes that your reward function needs to be a linear combination of a set of features. And the second is that usually those features are known. Like usually in all of these papers, they assume that they know these features for whatever approach they do. And if you don't assume that and you actually learn these features, because you can't learn them, then what you get is a second issue with successor features, which is that they're extremely bad the worse those features get, because you have the same feature for all of the successor features that you are learning, right? So if you estimate like the features for the environment, for the task space, and then you use that feature to learn like the successor feature for like the blue task, for the square task, and so on, you get this compounding effect of that same feature, because it is not optimal. It's going to give you potentially very bad successor features for any task you learn. And actually, in the generalization in reinforcement learning paper that I talk about, I have, because in their paper they have like bounds on the optimality of generalized policy improvement. I actually show that unless the current task is not the same task you have seen before in your lifetime, actually the bound is useless. You will get as worse. The optimality of that approach will be as bad as the worst possible value function you can have. Right? So like, for example, in the discounted setting, the worst possible value function you can have is the reward all over 1 minus discounting factor, right? So like the maximum, because you have the discounting factor, you take the geometric sum of that, and you get like maximum rewards at every single step. That is your upper bound on the value function. And their bound is actually worse than that upper bound if the current task is not a task you have seen before. So that is something that I didn't know before when I read their paper, because like it looked cool, but then when I was trying to do the proofs for the generalization paper that I did, and I was trying to use their proofs to kind of make mine easier, I actually realized that. So that is one problem, that their proofs currently are trash. The second problem is practically, you will still, so in terms of proof it is trash, but in terms of practice, you will still say that that generalized policy improvement approach will give you nice improvements, but you lose these guarantees of optimality, which to me I think is a second biggest issue, which is if we are trying to get to a point where our agents get more and more generally capable, we want our approximations from we want the approximations, or we want what we are trying to optimize for at least that to be known, like for at least that to be guaranteed to be the correct thing to try to optimize for, right? Like even if in practice we cannot get optimal value functions, even if in practice when we do this intersection, it doesn't give us optimal policies because we're doing functional approximation. At the very least, we know that we are guaranteed that we are doing the correct thing. We are learning the correct type of value function. We are doing the correct type of operations over them, because we know that in the case where they are optimal, they will actually give us the correct thing, what we want. So that is to me the second main thing. Now there's a number of other things that issues that I have with that line of work, but I think that is kind of like the main ones. But I'm not completely discounting that line of work. I think that the success of future idea is like very cool, but not for this type of, so they have been pitching it so far as being this kind of like, so they have been pitching it with generalized policy improvement and generalized policy evaluation for this type of like transfer learning approach. I don't think that is the correct application for success of futures, because it has all of these issues. But the idea itself of amortizing, assuming that your reward functions are going to be linear, and then learning these successor futures over the environment that you can use to get the value function for any linear combination of rewards is actually like interesting, and it's useful for other stuff other than transfer learning.
I see. Thank you so much. And in which paper did you say you showed that the proof actually has a really bad upper bound? That one, the logical composition for. Okay, thank you. I'm actually going to give it a read.
Yeah, and just check that the title for the conference submission is generalization in lifelong reinforcement learning using logical composition. So I didn't give the correct conference submission title here. So.
Oh, okay. Thank you.
So I have a quick, probably last question if you have time. So you've proved essentially that this is the right operation to apply on the Q values, if the Q values are indeed the optimal Q values. Are you able to do any sort of numerical analysis about what happens if you don't have the optimal Q values? And is there any way, so you've the max and min operations, they seem sort of natural things to try, but is there any way of learning those, having sort of a neural network which themselves learns what may not be optimal if you do have the optimal value function Q values, but if you have something which is an approximation, is there a way to learn what the appropriate operation is?
That is very interesting. So at the beginning of that question, I was going to say yes, we have actually thought of that, but actually right at the end of that question, that's actually a cool idea that we haven't tried yet. So it would be a cool thing to try to learn something that is not necessarily the optimal thing to do when you have optimal value functions, but actually could be the better trade-off to do in the case of non-optimal value functions. Yeah, that's very interesting. One thing to add is that we actually did do proofs showing that even if your value functions are not optimal, even if they are epsilon optimal, using the min and max, and actually recently we did a modification on the negation operator that also preserves this property. You lose no optimality. So like when you do these operators, you still get an epsilon optimal value function out of that. That doesn't discount that idea though. I think that idea is still useful in the cases where maybe, because epsilon optimality doesn't necessarily picture everything about suboptimality, right? It's just like a nice way of picturing suboptimality that people use for proofs. But maybe practically, that could be a good idea. Yeah.
Well, I'd be happy to continue talking with you about it if you'd like. I think we probably have to wrap up now, but thank you so much, Geraud, for a really fascinating talk. It's clearly got all of us thinking a lot.
Thanks a lot.
Yeah, thank you very much. And yeah, I'm sure we will chat with you again sometime soon.
Thanks very much for the opportunity to present here, and yeah,
Pleasure.
see you guys in the future.
Thank you so much.
Cheers.
Thanks. Bye.